Okay.
Okay, today we're happy to have Csaba Csaki all the way from Cornell to tell us about crunching away the hierarchy problem.
Thank you very much. So it's great to be here, at least virtually. Hopefully soon I'll be back for my annual talks there in person. So I would like to talk to you about the work that we did. I will mainly focus on the first part, the solution to the hierarchy problem, but there is a version of it that is also related to the cosmological constant problem. I don't think I will be able to get to that part, but maybe, just give a few words about that. So this was done. The first part was in collaboration with Raffaele Dagnolo, Michael Geller, and Amin Ismail, who is my student. And the second part was with Itai Block. Itai is a Tomer student in Tel Aviv, and Michael Geller, and then Tomer. Okay. So, oops. Sorry. Very good. So I guess you guys know all about this, but just a quick reminder. So we are going to be talking about the hierarchy problem, and the hierarchy problem. Probably the best way to phrase it is that
Csaba, your slide is not advanced.
It didn't advance?
No.
Okay. Let's go. What the heck? It doesn't advance for you? You don't see any?
The last few talks I've been to, everybody had problem advancing their slides. I don't know if Zoom changed something or what. It's weird.
I don't know.
Do you want to just try reconnecting or
Bring
something?
your shared window to the front. Okay, let me try to stop sharing. And then let me try it again. It has happened to me once before, and then what I needed to do is I turned off Zoom and turned it on. So if it doesn't work now, then I'm gonna have to do that, unfortunately. So let's try it now. Let's see. Play. Do you see it moving or not?
No, it's still on the first slide.
So why don't I just quickly turn off Zoom and then rejoin, or I don't know what.
Yeah, go ahead.
Okay, sorry. Okay. How about now?
Yeah.
Yay, good. Okay, sorry. Very good. So I guess everybody knows this, but it's useful to just emphasize that we are talking about the hierarchy problem, and the issue is that all the elementary scalars are expected to be ultra heavy, and the reason is that their masses are not protected by any symmetry, unlike the case for the fermions or the gauge bosons, and they will be sensitive to any UV scale physics. So when we draw these diagrams, the lambda, what we call the cutoff, is basically the stand-in for the mass of whatever new particle can appear at a high scale. So if there's any physics beyond the standard model, that will eventually expect it to be feeding into the mass of the Higgs boson, and that is expected to give you a correction to its mass. Oops. Okay, very good. So then the question is how to solve this issue. And of course, this is one of the things that we have been, or the main thing that we have been trying to explore over the past maybe 3 decades. And the most common approach that we have been trying to use was the symmetry-based approach. And the expectation is that there's some new physics at the TeV scale, and that new physics is something special, not just an arbitrary new physics, but it is of the form that it will shield us from UV corrections beyond the scale of that new physics. So that particular kind of special physics that can shield us from the corrections beyond that scale would be either supersymmetry or compositeness / extra dimensions. And typically in these approaches, you would expect to have new colored particles showing up at the TeV scale, in particular, so-called top partners. Okay, and these are not observed at the LHC. So these top partners, so they will, right now these models are under pretty serious stress. So I just put here one slide about the bound on the top partners, and you can see that, and this is not the final run to analysis, but whatever I found a year ago when I did these slides, you can see that bounds on top partners are now starting to dip over a TeV, depending on exactly what the decay rates are. So it's slightly model dependent, but the bounds are basically over 800, 900 GeV and can go all the way to 1.2 TeV. Okay. So that's the status of the symmetry-based approach. Now, it's not completely airtight. There are ways to avoid this. For example, neutral naturalness is one of the really interesting type of approaches that the twin Higgs type of models of Chaco and Ronnie, those are very interesting. And of course, we are trying to explore those as well. So they are still possible. They will have some deviations in the Higgs coupling. So, we are trying to find ways to test those as well. But, it's just, it's just to tell you that, of course, these arguments that colored particles are not observed is not totally airtight. So we are not completely giving up on the symmetry-based approaches, but it's, it's getting harder and harder to squeeze through, smaller and smaller holes, basically. Okay, so then, there is another really interesting direction that, was restarted, I guess, I don't know how many years ago it was, maybe 7, 8 years ago, what I would call the cosmological selection or the relaxation-based approach. And so in this approach, the correction to the Higgs mass would not be suppressed at all. And in fact, what would be happening instead, for example, in these relaxion type models, but there are other versions that are playing on similar kind of approaches, is that actually, through the cosmic evolution of the universe, we would actually be testing out, the different values of the Higgs mass, and something particular would be happening that would select the right vacuum for us. So for example, in the case of the relaxion, there would be a, maybe a phase transition happening around the time when the, when the sign of the Higgs mass squared is just flipping, and it would, for example, stop the evolution. And there are other versions like N naturalness. There's another selection criterion there, and I think this is a really interesting direction. The models, as far as I can see, are really baroque, and the parameter space that is corresponding to successful models are very, very unusual. They may be technically natural, but the choice of parameters is pretty weird. But I don't want to say anything bad. It's something new, and people should try to explore these a lot more and come up with realistic versions of them. Now, the third one is the antropic approach. And so in this case, what you have is you have a multiverse, and you have many different patches of the universe. And the assumption is that each patch has a different Higgs mass, and all of them are assumed to have order 1 quartics. And the usual assumption in this antropic approach is that only the patches where the Higgs mass is actually very small can support life. Otherwise, there would be no chemistry, for example. So that would be the standard argument for these. And one of the biggest problems that so this is a very nice story, but one of the biggest problems of this approach is that it's very hard or impossible to ever think of a way to experimentally verify this. So that's what I find is the biggest disadvantage of these antropic approaches. But it's certainly, is it possible that that's the way things are? Yes. Now, of course, it also has different variations, where you have, for example, split supersymmetry, and it's it's a combination of these. Now, what we were trying to do is sort of come up with a different approach that is somewhat distinct from each of these 3 that I have outlined for you before, but it's basically going to be combining I would say the best of the aspects of each of these different approaches. So there will be some aspects of the antropic approach in the sense that we will be still assuming that we are starting out with a multiverse where there are various patches, and they will each have a different Higgs mass or a different Higgs VEV. But we will also be taking some stealing a little bit from the dynamical approach, where there's some sort of a selection mechanism here. So what we will be assuming in particular for the solution to the hierarchy problem is that we have a multiverse, just like the antropic approach, but in addition we have a hidden conformal field theory, a hidden CFT that is spontaneously broken, which is producing a light dilaton. And in the particular approach that we will have a 5D version of this, that will be represented as a radion in RS models. And what we would be saying is that actually, the CFT has a very large negative vacuum energy. Okay, so the true ground state of the CFT, of this broken CFT, would be like a Goldberger-Weiss type mechanism, but its vacuum expectation value there would be very large and negative. So the expectation would be that if you were to sit at the true minimum of this CFT, then the universe would be very short-lived. So you would actually be crunching very, very quickly if you are actually reaching the minimum of your CFT. Okay. Oops, sorry. So this is, just the little picture. So, there's some CFT, there's some spontaneous breaking of the CFT happening. You are reaching the minimum of the CFT, and the minimum here is large negative, and it's so large, is larger negative than, for example, the inflation scales or whatever. So your universe is just going to be crunching very quickly. Okay. And of course, if this was the whole story, that would be bad, yes, because we wouldn't expect to have a long-lived universe. But there would be some additional. So what we are trying to do is to make sure that there's some sort of a selection mechanism that is going to let vacua that have a small Higgs VEV actually live long, and the other vacua where the Higgs VEV is very large, they are going to be just flowing down to the true CFT vacuum. Okay. So what we will be assuming is that this CFT, whatever, the CFT matter, I call it techniquarks, but you can call it whatever you like. They are actually charged under the ordinary SU2 electroweak symmetry. And that one is actually going to lead to an interaction between the dilaton and the standard model Higgs. Okay, so that will be the crucial assumption, that that the dilaton potential won't just be the trivial, the usual Goldberger-Weiss potential that we are assuming, but that there will be some mixing terms between the Higgs and the dilaton. And we want the potential to be such that there will be a second metastable minimum in the potential showing up if the Higgs VEV is sufficiently small, but non-zero. Okay, and if the Higgs VEV is large, then we want the second minimum to just disappear. Okay, so that will be the, basically our way of trying to solve the hierarchy problem. So that will be our selection mechanisms, that the vacua that correspond to large Higgs VEVs, they are just very short-lived. So those patches of the universe are going to be crunching in a very short amount of time. And the ones where you have a small Higgs VEV, by small I mean the small compared to other large scales, so of the order of the TV scale or smaller, then those will actually be long-lived. Okay, so then the expectation will be that after a long period of time, only patches of the universe with a small Higgs VEV will actually be existing. So in that sense, it's different than anthropics, where, in anthropics, no matter where you go, you will always have all of these universes present, and you will have to argue about, distributions or, why you live in a particular one. In our case, we do start out with these many patches, but we just dynamically crunch away the vacua that, that are leading to sort of unsatisfactory universes. And after a long period of time, you are only going to be left with the realistic small Higgs VEV, and those will be the ones that will be dominating the universe after sufficient amount of time. Okay, so here's a little cartoon where I'm just showing you that you do have the usual Goldberger-Weiss type minimum, but if the Higgs VEV has the sufficient size, so something of the order of the TV scale, then there could be a second minimum showing up. And of course, we will have to double check that the tunneling rate from the second minimum to the true minimum is long enough. And then the expectation will be, the hope will be that at this new minimum, the cosmological constant could be very small, so that, for example, normal inflation can happen. So here we are assuming that the minimum is very large, so it would overwhelm inflation and everything. So it will, if you get here, you just crunch. And this one would happen at very small cosmological constants. So it could still be a reasonable evolution of the universe could happen here. Okay, very good. So the particular setup that, to be very concrete, we actually constructed a full realistic 5-dimensional RS Goldberger-Weiss type setup for this scenario. So the capital phi would just be the usual Goldberger-Weiss field, which is a scalar that is living in the bulk. And then the location of the IR brane would be identified basically with this dilaton field or the radion field. And so as usual, the expectation is that on its own, without incorporating the Higgs, you are just going to get an effective dilaton potential after you integrate out the bulk of the extra dimensions. So you get the usual chi to the 4th term. So this chi to the 4 is coming from the mismatch, a slight mismatch of the IR brane tension from the bulk cosmological constant, and then the usual chi to the 4 plus delta type term, which would be the effect of a small explicit breaking in the CFT. So in practice for the 5D theory, that would be usually corresponding to a small bulk mass for the Goldberger-Weiss field. Okay, and one thing, just for the experts on this, so we are going to be using the notation where the dilaton is not canonically normalized. So we are just going to be literally using the location of the IR brane as the dilaton, and then you will always have to remember that actually, in order to get a proper canonical normalization for the dilaton, you have to remember that there's a prefactor in its kinetic term, where n is related to the number of colors in the dual CFT. And that one is related to the ratio of the bulk curvature scale to the 5D Planck scale. So it's related to this m star r ratio. And as I said, the chi to the fourth term is the usual scale invariant dilaton potential that you're usually having in any spontaneously broken CFT. So that's allowed by the symmetry, even though the dilaton is a Goldstone boson, but because it's corresponding to broken scale invariance, a chi to the fourth term is allowed. And as I mentioned, the chi to the 4 plus delta term, so that's the effect of the small breaking due to the bulk Goldberger-Weiss field. Yes, the bulk mass for the Goldberger-Weiss field. Okay, so far that's the standard story from 20 years ago, or how many? So the thing that we did is, so we added a Higgs in the bulk, and of course, we are not the first to add the Higgs in the bulk, but we are doing it now. This one is going to be done in a very different way than people are trying to usually use RS. Okay, so we are adding a Higgs in the bulk with a mild profile. Okay, so for us, it's not going to be important for the Higgs to be exponentially very strongly peaked on the IR brane. So that's the usual way RS models are used to solve the hierarchy problem, is to make the Higgs composite, make it to be peaked on the IR brane. Instead, for us, the Higgs is going to be mainly elementary. Yeah? So that would be sort of along the lines of this is in some sense a multiverse model where the different patches are just scanning over the different values of the Higgs mass parameter. So we just put a bulk mass, an arbitrary mass for the Higgs onto the UV brane. Okay. And again, we are assuming that within the different patches, this UV brane Higgs mass and the Higgs potential, they are widely varying in the different patches, just like you would normally do in multiverse theories. So they could be whatever, as large as whatever your cutoff scale of the theory is, and we are going to be discussing later on, how large the cutoff would be. Okay, and then of course the important part is that we are also going to be putting some localized interaction terms of this bulk Higgs onto the IR brane, because that's what will then eventually give you the interaction terms, the mixed terms, the terms in the potential that are mixing up the Higgs and the dilaton field. And so if I didn't add any localized terms, I wouldn't. I mean, of course, there could be maybe, because you cut it off, and there could be a little bit of a dependence, but it's mainly from these localized terms that you are going to get the mixing terms between the Higgs and the dilaton. Okay, so
Can I ask a question?
Yes, of course.
So as you're scanning the Higgs mass, are you holding the IR scale fixed? Scale of the IR brane, and what is that scale? Is it? That's what I'm asking. Is it varying? Is it fixed? What is it?
So it's going to be set by the dilaton potential, yes. And I'm going to minimize the potential to find out what the IR scale actually is. Yeah? So I'm trying to, I'm going to generate a potential for you that is now a function of both the dilaton and the Higgs, and I'm going to try to find the joint minimum of both of those, yes, and then try to see, in which situations am I going to get a long-lived universe, and I want to make sure that that one is. So I'm not putting it in by hand, yes. I'm gonna, it's gonna be the output of a normal Goldberger-Weiss type of potential, Yes, and so it's going to be an output for you.
Okay, so maybe you'll explain.
Yeah, of
what the
course. I mean, the main thing will be to minimize this potential. Yes, so that's the, to try to convince you that such a potential actually exists. Yes, that with reasonable parameters. So I'm going to try to tell you exactly, what terms we are putting in. So that's where I'm getting here. Yes, what terms I'm assuming are present on the branes, and then try to find the minimum of this potential. Okay, so so first of all, the important thing is that so now there will be a z dependence for the profile of the Higgs. Yes? It's just because you have a bulk mass for the Higgs, so there will be a mild z dependence. You don't want it to be completely z independent, yes, because then it doesn't, then you're not going to get a dependence on the dilaton. So our aim is to make sure that there is some Higgs the Higgs profile will influence what exactly where you are minimizing the dilaton. Okay, and so there will be a slight z dependence on so this is the z dependence of the Higgs profile on the position of the extra dimension. Yes, and so again I'm going to add just as a UV source. So this is HUV. So that's just from the fact that I added basically my standard model Higgs potential on the UV brane. Of course, because I added additional localized terms, they will give you small corrections. So what you add on the UV brane is not quite exactly the standard model Higgs potential, but we will make sure that eventually we'll check that that's sort of a small correction to the standard model Higgs potential. So for now, we are just treating it as adding a source for the Higgs on the UV brane, and then just let it evolve along the extra dimension, and then add some localized terms on the IR brane. So for example, I can add localized terms that are a localized quadratic term or a localized Higgs quartic term on the IR brane. Okay, so now, because again the Higgs VEV has a little bit of dependence along the extra dimension, yes, this localized quadratic term, even though I just add an h squared term on the IR brane, now if I look at how does that depend, in terms of the UV source for the Higgs, what kind of induced term does it give me? It will give me a term that also depends slightly on the position of the IR brane. So it will depend on the dilaton. So if you add just a localized term, yes, then you will get this h squared times chi to the 2 plus alpha, where the alpha is related to the bulk mass parameter of the theory. Okay, and then for the quartic, you're going to get an h to the 4 chi to the 2 alpha, and then it turns out we will actually need 3 different terms. So we will need 2 different h squared type terms in order for this mechanism to be successful. So you can just get a localized term that where you're also, for example, mixing it slightly with the Goldberger-Weiss field on the brane. So you just need a second different power that is showing up here. Okay, so that will be our assumption that we will add these additional localized terms, and each of these, if you want, you can get relatively simple CFT explanations for these terms in the potential to show up. So the usual story would be as as Ricardo and Zaffaroni explained for their famous paper in the CFT explanation of the Goldberger-Weiss mechanism. So you would have one operator that is dimension very close to 4, yes, but 4 minus epsilon, and then this epsilon is the extra piece that is giving you the chi to the 4 plus epsilon term in the usual Goldberger-Weiss potential. In addition, basically what we need to assume is that within the CFT, there is an operator that is now going to be a doublet of SU2. Not usually, you pick a singlet, that's the usual Goldberger-Weiss operator, but now we are going to pick a doublet of SU2, which is now close to dimension 3. Why close to dimension 3? Because when I contract it with the Higgs, that's when the two together should be close to dimension 4. Okay, so that's where this extra parameter alpha is coming in. Yes, the combined the CFT operator times the Higgs, that should be a close to dimension 4 operator. So the deviation of that from 4, of this combined operator, that's basically what we call alpha, or I don't remember why we called alpha over 2. I guess we didn't want to carry other factors over here. So that's basically the CFT explanation of the setup that I showed you before with these localized terms. And so the kind of Higgs potential that you're going to get is, so here's your usual Goldberger-Weiss potential. And then, as I was showing already in the 5D picture, you're going to get these additional terms that are mixing the Higgs and the dilaton with each other. Okay, so that's going to be the main part of the story. And so we have this full potential, the standard model Higgs potential on the UV brane, the usual Goldberger-Weiss potential, and then this additional induced piece, which is going to giving you the mixing between the Higgs and the radion. And so now what we are really interested in is what happens. So this is the shape of the Goldberger-Weiss potential far away from the origin. And you can see that it is going to give you a very large negative minimum, so as we expected in general. But what we are interested in is the behavior here very, very close to the origin. And what we would like to achieve is that have the parameters of this theory chosen such that if the Higgs VEV is relatively smallish, then there is this additional minimum showing up. So this is a zoom in here. So you can't really see on the large picture that these three curves are actually distinct from each other. So these are these potentials for some chosen values. I don't remember anymore, what these parameters are, but for some chosen values of these couplings for 3 different values of the Higgs VEV. So you can see that it's pretty sensitive to what exactly the Higgs VEV is. And you see that for 175, there is still a second minimum, and then there is then there's an inflection point, and then you are going to lose the second minimum once the Higgs VEV is becoming larger than a critical value. Okay, so you can go ahead and try to actually analyze what the property of this potential is in order for you to get a critical point or an inflection point in the theory. So because you are analyzing it really, really close to the origin, the Goldberger-Weiss potential is going to be negligible there. And you can basically just rely on these 2 h squared terms. Okay, so you can just rely on these 2 h squared terms, and you can more or less minimize those two. And then you can find what the value of the dilaton itself is at the inflection point, and you can find what the value of the dilaton is at the actual minimum, at the second minimum here. Okay, so you can just minimize these potentials, and you see that it's basically this critical value depends on these 2 different quadratic terms that you are playing out against each other. Okay, and then you can find then what the value of at the minimum is. So for that one, the lambda 4 is also going to play a little bit of a role. And then of course you're trying to see that you want your Higgs VEV basically to be identifying that roughly with the critical value of the Higgs VEV, where the second minimum is going to be disappearing. And so you see that this one here, this is kind of a very very familiar formula for those people who have been playing around with RS and Goldberg-Gervais. So you get a very similar looking formula as you usually get in Goldberg-Gervais for the explanation sort of the hierarchy, yes, in the sense that it's this 1/epsilon's power of the ratio of two almost order one-ish couplings, yes, but so you need this epsilon to be small as usual, and then you need a little bit of a hierarchy within these two quadratic couplings of the Higgs in order to get in order to get a hierarchy between the value of the Higgs VEV, yes, and then whatever the generic scales in your theory are, the K, the ADS curvature. Now the thing I want to emphasize here is that you could say, oh, this is just RS, but I want to emphasize this is really not RS in the sense that for us the Higgses are elementary particles. So we are not achieving here a hierarchy by making the Higgs composite and then localizing it on the IR brane. So here the Higgs is elementary. There's a little bit of a shape to it, but the Higgs potential, the standard model Higgs potential, is added on the UV brane. So there is a sensitivity there to the UV scale. And again, we are trying to play this game with crunching away the bad vacua by making sure that the dilaton potential and basically the value of the vacuum energy is going to be very sensitively dependent on what exactly the Higgs VEV is. Okay.
So alpha doesn't appear on this slide. Are you assuming that it's much smaller than epsilon, or is there some reason why it drops out?
So let's see. Yeah, so we just assume that it's pretty small, I think, and let's try to see. Sorry, here was the right formula here. Right. So the reason why alpha doesn't show up is because it's basically what the critical value is you're trying to compare the two terms that are both quadratic. And so both of them have an overall alpha dependence. So in the relative value, the alpha is going to drop out. So that's what is driving whether or not you're actually going to have a minimum. So when you look at this potential, whether or not you will have a second minimum will depend on comparing these two terms. Okay, and then what exactly the value of the potential is at the minimum, the third one also will play a role. But basically, you at the minimum, you are balancing these two. It's a little bit like a racetrack model where you have a slightly different dependence, 2 plus alpha and 2 plus alpha plus epsilon. So in that sense, again, it is very similar to Goldberg-Gervais, where you were comparing 4 and 4 plus epsilon. Okay, so that's why alpha to leading order. I'm sure there are small corrections, but to leading order, alpha doesn't show up in this in this particular expression. Okay, very good. So so very good. So then the question is, so what will be the consequences of this? So first of all, so we have the Higgs in the bulk. So we won't be able to get away without putting the SU2 gauge bosons into the bulk. So that's a direct consequence of our setup. So at least the SU2 gauge bosons, so the W and the Z, are going to have KK modes. So those, we know the LHC bounds on those are 3 to 4 TeV. Okay, so that is telling you that that the size of the radion of the dilaton at the minimum. So this is what roughly, I guess, what Marcus was asking. What tells me how large the extra dimension should be? Yes. So this is where we are saying, okay, at the minimum, the size of the extra dimension should be at least 3 or 4 TeV. Otherwise, we would see these KK modes for the W and the Z which haven't been observed in the LHC. So that tells you that there's still a little bit of a hierarchy here. Yes. So the critical value of the Higgs VEV, yes, we know, well, that's what we are going to be identifying roughly with the ordinary Higgs VEV. So that's 170 GeV. And then there's the size of the extra dimension, which is, again, 3-4 TeV-ish. So this is, there is at least a factor of 10 or 30-ish showing up over here. Yes. And so now if you look at the actual relation between the minimal value of the value of the radion at the minimum and the Higgs VEV, you will see that it will involve at least a little bit of tuning still. Okay, so you will see that these couplings that I have added, and I have written them in a form where they would be naturally of order 1. Everything else has been scaled out, but still, they can't be of order 1. And in fact, so you could say, okay, maybe I can put here a big lambda 4 to make this little hierarchy better, but that you cannot do either because you want to avoid a lambda pole. So this lambda 4 is a quartic on the IR brane, and that would. Marcus has a question. Yes, Marcus.
Yes, sorry. So I just want to see if I understand. So
yes,
when suppose we're in one of these minima where the Higgs VEV is of order the weak scale.
yes.
On those minima, the IR brane is also has a natural scale around the TeV scale. Is that correct?
So that's what we are trying to achieve. Yes. So that's what we are trying to achieve, and then we are trying to see what kind of parameters do we need for that.
Right. Okay.
And
before we get to the parameters, I just want to understand.
yes. So chi-min, again, H critical should be 175 GeV, and chi-min, again, because of the KK modes of the W and the Z, should be at least 3 to 4 TeV.
Right. I'm just really concerned about the big picture. So I'm not worried about
So it should be at least, it should be, again, electroweak-ish, but heavier than, the inverse Higgs VEV. So, right, that's the little hierarchy. And then now the question is, can I get that very easily from my potential? So,
fine. But can I ask another question? Though?
Yes.
So, sorry, but okay. So I'm just trying to understand the big picture. Okay. So Goldberger-wise is a mechanism where I try to find a minimum for the radion, the Higgs, and whatever, where all those scales are a TeV. This
right.
mechanism, it looks like it is very similar in the big picture sense, that it's a mechanism to robustly get a minimum of around a TeV, but then also with this much lower global minimum.
Right, exactly.
Is that fair?
Yeah, I think so, yes.
So,
right. So you want to have two
landscapey thing. It's a robust mechanism. It doesn't, because I just had the impression from the first part of your talk that the landscape was going to play some big role.
Yeah, so it does, yes,
like
because
that's why I'm asking.
It does play a big role, yes, because what we are trying to say is that if the Higgs VEV is larger than a critical value, so as you saw in this plot, if the Higgs VEV is, let me just try to. So if the Higgs VEV is bigger than, let's say, 200 GeV, then the second minimum just completely disappears.
But what are you varying and what are you holding fixed when you say that? Because there's a lot of parameters here that are going into making this thing.
Right. So I'm going to hold. Right. So. Yeah, so all of these parameters in principle are going to be changing, yes. But the main effect of how large the Higgs VEV is, as that is going to be set by the UV brane parameter, UV brane mass parameter of the Higgs. Okay, so that's where you're scanning. That's what the scanning mechanism is. So what is the magnitude of this Higgs VEV is mainly going to be determined by what you put in to the to this elementary Higgs on the UV brane.
So, but then why aren't you getting 100 TeV or 10 to the 4 TeV or whatever, some other number? Why are you getting 10 to the 2 TeV when you scan? I mean,
right. So the answer is that the 10 to the 4 does not produce this minimum. Yes.
for
You
any
just
other choice of these parameters, even though you don't have any 100, 200 GeV put in, the VEV could only be 200 GeV. Even
I
when
mean,
you
it could be
scan
100. It could be 100 or 50 or 10.
Right, but it couldn't be 10 to the 3.
But it couldn't be 10 to the
4,
exactly.
5. When you
Exactly.
scan all of
That's
those parameters,
so that is our mechanism. Yes, that it couldn't be 10 to the 5.
why not?
Because if it was, you wouldn't have the second minimum, and you would just fall down, and you would crunch the entire patch.
When you scan all your parameters, every parameter in this Lagrangian is being scanned, and yet you only have a minimum in a small region around 100 GeV.
So okay, that's a good question. Which parameters are we scanning? So the way we have imagined is that we are scanning the parameters of the UV brane on the UV brane, and that we have one uniform CFT. So in our scanning procedure, we have kept these other couplings for now fixed. I mean, those are in principle, they are order 1 parameters. So, it shouldn't be
the ones that are giving you this racetrack mechanism, and that's what's leading to this 100 GeV scale. And
right.
Then if there's a mismatch somehow between that and the other couplings that
so for example, the thing that we are crucially not scanning, yes, the thing that is the alpha and the epsilon, yes. So those are the crucial things. So those we are not scanning. Yes. So that is of course crucial. If we scanned the epsilon and the alpha, so basically what we are saying is that we keep the CFT fixed, and we are scanning the elementary sector completely. Okay, so that's a good question. Is that a reasonable thing to do? Yes. Can I actually have a model of?
I'm trying to argue with you. I'm just trying to understand.
No, I'm telling you that's a reasonable question.
I think you have a racetrack type mechanism that picks out. Tell me if I'm wrong. I'm just trying to understand what you're doing. You have a racetrack type mechanism that picks out the TeV scale or 100 GeV scale.
Right.
Okay, and that you're assuming is not scanned. Then you're scanning other parameters, and if those are not in some small range, then that racetrack mechanism does not give you a local minimum.
Right.
So like
exactly.
The racetrack mechanism would be some sort of solution to the hierarchy problem, but it only works when you scan these other parameters. When
exactly. I think that's a fair way to say it. Yes.
Okay.
I mean, it's basically we took technically, yes, something that is, like you say, like a racetrack, which is like the Goldberger wise, yes, to generate a hierarchy, yes, and like you say, yes, so it works only if the scan parameter is within a particular range, yes. I think that's a fair way to summarize, yes. All right, so. Very good. So then the question is the choice of parameters that will then give us a fully realistic model. Yes. So again, I explained what is constraining the size of the extra dimension. So that's these W and Z KK modes, and so you want to make sure that the actual minimum is quite a bit higher than the Higgs VEV itself, than the critical value of the Higgs VEV itself. And then you have to look at what exactly is the expression that you get from your potential. And again, it turns out that you have this ratio of these couplings that is showing up here, but then this coupling itself you cannot jack up too much, because it is a quartic self-coupling that is on the IR brane. So you can do a simple estimate for a Landau pole, and you find that this, it cannot be more than a few, maybe 3 if you push it really hard. So it tells you that still, some of these couplings, some of these IR localized couplings that you would naturally want to put at order 1, if you just do naive dimension analysis, in order to get the right hierarchies, you still, some of these couplings have to be relatively smallish. So it turns out that, for example, this lambda 2, instead of being 1, it has to be 10 to the minus 2. Okay, so you are still going to get this, percentage level tuning that that unfortunately we are getting more and more used to from little hierarchies. But again, it's showing up in a totally different way than in the usual solutions to the hierarchy problem. And then there's one more thing that you want to make sure that I mentioned to you, that I'm analyzing this theory at very small values. So you want to make sure that the pieces of the potential that you're actually minimizing are the dominant pieces. So you have to make sure that the Goldberger-Weiss couplings themselves are relatively small. Okay, so that you are not still dominated by the Goldberger-Weiss couplings at the small values of the potential. Okay, so that's the story. Now, the important thing is that once we swallow all of this, then we actually have a very nice prediction here, namely the fact that, of course, now the hierarchy problem is very strongly related to the presence of this particular type of dilaton potential, which is now going to be very light. And it's going to be, so you saw that all of these terms in the potential, they turned out to be very small. Yes, so it's going to be a very weakly coupled particle, and we can actually estimate, at the minimum of the potential, what the value of the mass of the dilaton is. So we can just go ahead and minimize it. We can sort of do this even semi-analytically. Well, first of all, there will be a mixing between the Higgs and the dilaton. Okay, so that mixing is again related to kind of, this quantity that is giving you the little hierarchy problem. So that's actually going to be a small mixing angle. So something of the order of 10 to the minus 3 to 5 or something of that order. So it's a very small mixing, but something that can have important experimental consequences. And then you can go ahead and calculate what the actual mass of the dilaton is. And by looking in detail at the particular potential that we had, it turns out that there's an upper bound and the lower bound on the mass of the dilaton. So it's something, it's a light particle, so it's something that the upper bound, you can see it's something of the order of 10 GeV-ish, and the lower bound, so this is, once we did the actual numerical studies, is something of the order of 100 MeV. Okay, so that's pretty nice. And as I said, it will be mixing with the Higgs. So the mixing angle is something of the order of 10 to the minus few, between 10 to the minus 2 and 7. And it will inherit all the interactions of the Higgs due to this mixing, yes, but with a very small mixing angle. So whatever interactions the Higgs has, the dilaton has it too, just suppressed by this mixing angle factor. And yes, Marcus.
Sorry, what is it that's protecting the light dilaton mass? Is it just very, very weakly coupled to
right
everything?
So we had, so it's the choice of the parameters in the potential that we need in order to get the realistic values of the minimum. Okay, so it's, sorry, here is my potential here. So you have this plus the, okay, so here is the full potential, yes, and it's just small values of these couplings. So so there is a little bit of a hierarchy as why are these particular values not order 1? Yes, so that that we are not explaining. And so I'm not claiming that there is totally no hierarchy put in by hand here. Yes, certainly it's much smaller hierarchies that I had to put, these couplings that would be order 1, I put them 10 to the minus 2. And, so that's the kind of, suppression that you have over here. Now, we are of course thinking if we can make this better. So I may say something about that at the end. But anyway, so we have this small coupling, so small mixing with the Higgs, and in addition there are a little bit of direct couplings also, just because the dilaton is a bulk field, and whenever you have other bulk fields, there will be direct couplings from the fact that the dilaton is partly living in the metric tensor. So whatever fields are in the bulk, so for example the gauge bosons, they are going to have it. Now it turns out that for the massive gauge bosons, this direct coupling to the Z and the W is actually subleading to what you would be getting from the coupling from the mixing with the Higgs. But for the photon, this is actually the leading direct coupling, the direct one. Okay, so then what we did is we now did a big scan, many parameters. So we were varying the parameters around the region where we know that the realistic models are going to be showing up. So we just wanted to see how widely we can vary the physical parameters of the theory. So again, so we imposed, of course, that there's a metastable vacuum that is located at a large enough where the KK scale is large enough, and that the critical Higgs mass is small enough so that the Higgs VEV is natural. We ensured that the minimum is a true local minimum of the two-dimensional potential. So we checked that it's an actual minimum. Yes, so we didn't just set the Higgs VEV to the standard model value and then minimize. So we checked that it's a true minimum of the two-dimensional potential, and made sure that the bounce action is large enough so that this metastable minimum is long enough lived, so that the tunneling to this crunching minimum is actually sufficiently suppressed. Okay, so we did several of these scans, and then here are just the results of what the couplings of the dilaton are going to be. So here you see again the kind of masses that we got in the numerical scan. They never even reached 10 GeV, so we couldn't get for the realistic points, we couldn't get much above 7 or 8 GeV. So that's about the upper bound, and the lower bound again was something of the order of a few hundred MeV. And so here what you get is the coupling to the various standard model particles, including both the coupling through the mixing and the coupling through the direct interaction with the bulk photons. Okay, and then here are the constraints. So the different colors are just two slightly different scans. So we chose two different values for the RS bulk. So this N parameter, which is telling you, what the ratio of the bulk curvature and the bulk Planck scale is. So we varied it, and so you can see that they were sort of, we presume, if we change it continuously, we could probably, fill up all of this region over here. So you can see that, in fact, these are actually not experimentally excluded yet. The strongest constraints are from rare B decays, both at LHCb, and then the dashed lines here are future LHCb projections. Okay, and there are two different colors because actually you have to scale the LHCb bounds slightly differently depending on what the kinetic term of the dilaton is. So the blue bound applies for the blue points, and the red one or pink one, whatever, that applies to the red points. Okay, so you can see that actually, a good chunk of the parameter space, is some of it is already excluded by B decays, but some of it is, completely unconstrained or going to be slightly tested by future LHCb experiments. Now, one of the upcoming experiments, if there is, another Z factory, so you can have very precise tests for this model. For example, if you have a new Z factory at a circular E plus E minus collider, so that's the Terra Z, so that would exclude all of these points above these this dotted line. And then the region down here, so those will actually be tested partly by B decays or LHCb. You see the extended one. I think that's maybe I forgot. Maybe in about maybe in the next one, but I don't remember anymore exactly. How far out you have to go with the LHC to get these improved bounds, and also partly the searches for light hidden particles like Phaser and SHIP. You can see that they have some really nice coverage down here in the lower region, where the BDK bounds are going to be less effective. And then here, this is the constraint on the coupling for the photons. So there's things like E plus E minus going to 3 gamma and bounds like that. So you can see that most of the parameter space is still allowed here. But for example, again, the future circular collider, if it's ever built, as that would completely cover the parameter space over here. Okay, so again, the main experimental signal, which is really showing the heart of this mechanism, is the fact that there's a light dilaton. It can be observed, and some pretty large chunks are already excluded, and all of it hopefully will be covered in future experiments. Now, we do have KK-modes for the W and the Z, but they don't play a role in stabilizing the hierarchy. As the only reason we have it is because we put the Higgs in the bulk, but they are not there to cut off divergences or whatever. So we don't care how heavy they would be. The only reason we care is because we don't have LHC observations for them. We don't have top partners in this theory. The top could be completely on the UV brane. And again, I want to just emphasize again that the construction is based on an RS type model, but the Higgs is elementary here. So the physics and the signals are very different from the holographic composite Higgs or an MCHM type construction. Okay, so let me take just a few more minutes and talk about the cosmological constraints. So of course, we want to make sure that that the Hubble scale is actually not too high, so that the dilaton potential is actually still sensitive to the electroweak scale. So that is telling you that the scale of inflation actually shouldn't be super high. Yes, so there's an upper bound then on the scale of inflation in this theory, and then we want to make sure that the cutoff scale, whatever so that's the scale up to which we are going to be scanning the Higgs mass parameters, is going to be somewhat below that scale. Okay, and there are some other slight constraints on the theory, just making sure that the energy density in the true vacuum, the one where you are crunching, if you are not in the sweet spot for the Higgs VEV, is actually going to be negative. So that one is giving you basically a lower bound on what the ADS curvature is supposed to be for you. And you know, if for example the actual cosmological constant problem is solved by antropics, so here we are not trying to solve that one at all, yes, then the maximal CC shouldn't overwhelm the negative cosmological constant at the Goldberger-Weiss minimum, yes. So then, you know, in the scanning of the CC, of course, you know, we have to make sure that, you know, we are not pushing, you know, the minimum where we say we are going to be rolling and crunching. We should not be overwhelming that with a large positive cosmological constant when we are trying to solve the CC problem. So there will be a maximal value for you know, an anthropic solution of the CC problem. Okay, and then there's one more important constraint here that, of course, you know, we want to make sure that, you know, our patch actually is going to crunch both for large Higgs VEVs, but also for very small Higgs VEVs. Okay, so we want to make sure that the field actually rolls down to a true minimum. Okay, and it doesn't get stuck eternally inflating. Now, at large Higgs VEV, that's actually very easy because you can just check at a large Higgs VEV, you can check that the second derivative of the potential is big, and the Hubble constant that you have at the time, I already put a relatively strong bound on it. So you will truly roll down and you're not going to get stuck at some intermediate point if you have a large Higgs VEV. Okay, so now, of course, you also want to avoid not having a Higgs VEV. So you want to solve the hierarchy problem from both directions, because you could just say, well, you know, I can have a very large positive Higgs mass and I don't have a Higgs VEV, and I want to exclude that possibility as well. Okay, so now what happens if I have a zero Higgs VEV? So in that case, the situation is more subtle. That's because in that case, if I have a zero Higgs VEV, then in my dilaton potential, all the mixing terms are not effective for very small or zero Higgs VEV. And in that case, I only have a chi to the 4 term in just the usual Goldberger-Weiss type term, the chi to the 4 and the chi to the 4 plus delta. But at very small values for now the dilaton value, when the Higgs VEV is 0, yes, then I could get stuck there. So I could get stuck at the origin there and not flow down, not roll down to the actual minimum. So somehow I want to be able to exclude the region, you know, just around the origin for small, for zero Higgs VEV and for small values of the dilaton. Now, it turns out that this is a kind of story that is relatively easily solved, and it's something that people in other contexts of RS have been thinking about. So, for example, Geraldine and her collaborator von Harling have been thinking about related questions about the phase transition in RS models, and it turns out that you can just add an extra gauge group in the bulk, and that will actually make sure that, you know, the region around chi equals 0 is going to be excluded, so you're not going to be getting stuck there, and then you know, the story is going to, you know, just play exactly the way that you wanted. All right, very good. And what is this? Okay, so I think I'm going to stop here because is this a loop here? Okay, I think I'm just going to stop here. I have still, you know, a whole discussion, you know, what to do with this small chi region, where I'm worried that I'm going to get stuck here. So what you can do again here is add an extra gauge group in the bulk, and that will give you an additional piece in the potential that is going to make sure that you are, you know, that region with small chi is also going to be excluded. Okay, so I'm not going to explain all of that. If anybody is interested, you know, it's a story that again, you know, Geraldine was explaining. So I'm going to stop here. Again, I could give another talk, and I'm not going to try to do that now, about applying the same ideas to the cosmological constant problem. So until now, trying to crunch away the hierarchy problem. And we have played, and in fact, this is what we started out with. That was the original idea, to play the same game for the cosmological constant problem, and basically, find a crunching solution to that. And we did succeed with that. If anybody is interested, I can stick around and tell you a little bit about it. But I think other than that, I'm just going to stop here and pause for questions.
Okay, thanks. Questions? Joe.
Maybe it was implied in the last few things you said related to cosmology, but what happens to the crunched away regions? Do they leave behind some kind of defects, and are those
That's a good
inflated
question.
away, or what?
So we haven't thought about that at all. We are not really experts in quantum gravity, and so we just assume that the crunched region is like an empty shell that is basically it's a region that even though there's a coordinate there, but there's no region of space-time there at all. But that's a really good question. Is that a reasonable assumption? How to do that? I don't know how to do that calculation. So that's I would like to know if there are any experts on quantum gravity. What happens to the regions that are crunched? Is that going to be a problem? Can we sort of see the remnants exactly? I don't know. That's a really good question.
Okay, thanks.
Students, any student questions before Marcus gets another turn? Okay, Marcus, you're up.
So as I understand this, the main claim in this model is that if I hold all these other parameters fixed and I scanned MH squared,
Right.
then there's a narrow region for MH squared where I get this local minimum.
Yes.
First of all, just to make sure I'm following, and that region would be as tuned as in the standard model to get roughly, right? Parametrically, I'm guessing, yes?
Well, except
it's scanned, so it has to be scanned as precisely as
absolutely, yes. So you have to have a scanning mechanism, yes. So we
Right.
didn't try that, yes.
That's right, and it's just like in the standard model, right? Okay, and now, but it's a little, what I didn't understand, you presented the model and you gave a lot of formulas, but I have to admit I didn't follow. So I'm trying to understand the basic mechanism by which this minimum is somehow only there for this narrow range of MH squared. And so let me try to get at that with a specific question. So suppose I take MH squared to be very large and positive. Why don't I have a minimum near H equals 0? If I just take MH squared bigger and bigger, close to the Planck scale or whatever, why don't I get a minimum near 0, near H equals 0?
So again, so it depends, of course, on the signs of these couplings. Yes. So we are playing, these two couplings against each other. Yes. And you can just go ahead and check that there is a critical point below which there is a second minimum, and it's like a like you said, it's like a racetrack model, and
but you see, it's kind of weird if I'm not familiar with this model. I just put a gigantic positive MH squared term. I know it's in the ball.
UV brane, right?
On the UV brane, for example.
on the UV. Oh, okay. So you're asking, so H equals like 0. Okay. So
why wouldn't there be
in that case, H equals 0. Yes. So these terms have no effect at all. Yes. if you add a large, gigantic positive value, h equals 0, and these terms, they don't play any role. So basically, the only thing you have is this potential, yes? So the only thing you have to worry about, so that's what I was trying to say, that's something that you do have to worry about, is that you don't get stuck at the origin, yes? Because, you have a Hubble friction that wants to keep you there, yes? So that's the one thing that you have to worry about. But once you start, once you start rolling, yes, then you get there. So the only place that you have to worry about is not getting stuck at the origin. But I agree, that's a problem. Yeah. So that's, for this, we had to have this whole elaborate thing that I skipped at the very end of, adding another gauge group in the bulk and then making sure that, its beta function is such that, that you sort of, even if you don't have a, you don't have a Higgs VEV at all, you get nudged in the right direction.
I'm still worried about, sorry, maybe I'm just being stupid, but I'm just worried about a local minimum at the origin. I agree with Sincha's version. If I just add a h² term on the UV brane, it would add an h² term to this with a positive coefficient. Now for small h,
absolutely. So we have that, yes. So that is our full potential, yes. So this is our full potential, yes. And this sign again, we want to make sure that either way is good, yes.
So alpha and epsilon are negative or positive?
They are positive. They are small positive.
And then for small h, an h² term will dominate over them. If you go back to your previous potential, if I look as a function of h.
Right here, I have that. Yes, of course.
Okay, so
that's the standard model potential. Yes, that's the elementary standard model potential. Yes. So
then he goes to his deeply negative minimum.
Yeah, it just goes down to the, and then it crunches. Yes, that's what we want. Yes. It just flows down. There's no minimum here, and you just roll down. Absolutely. That is the mechanism. Yes, that is the mechanism.
Okay. Now, this is what I was trying to understand. So then I guess so let's see. So
for a small region here, there's a little bit of a dimple. Other than that, you just go down.
Maybe you need to draw a two-dimensional plot, one axis for the dilaton and one axis for the Higgs.
I'm trying to understand why the potential has that form. I guess the other general question, that was helpful. I'll have to think about it some more. I guess the other question I have is does this mechanism really need a light dilaton, or is that just your model? I mean, why does this mechanism require such a light dilaton? Is there
so again, so in our case, it was specifically to get the realistic parameters of the theory. Yes. So I'm not sure. So the light dilaton was a consequence of imposing all of these constraints. Yes, that imposing the constraints that I don't have a KKW and the KKZ that is below a few TeV, and yeah. So I cannot tell you for sure that there's no version of this model where the dilaton is not heavier.
But other approaches to solving the hierarchy problem with dilatons also end up down in this region. So
yeah, I would.
Not surprising.
We weren't surprised at all. But again, if you're asking me, do I have a proof that if you tinker around and you find some new ways for not putting in the constraints on the W and the Z, can I relax the bound on the dilaton? Maybe. So
I was just wondering if there was a physical picture. I mean, between a mathematical proof and parameter scans, there might be a physical picture that might indicate why this is happening. I was just wondering if there was something like that.
Again, I mean, so the best is basically, this is an approximate formula that is, that is giving, by that you get, and I think the second term is the Goldberger-Weiss, so you can neglect it. So you can see that there is a relation here between the, there's a strong suppression of the dilaton mass compared to the Higgs mass by this mixing angle. But yeah, I don't, beyond, that, I don't have a better, a much better picture.
If you allow very light WZ mode, you can make dilaton heavier, right?
I think that's possible, yes. That's possible. So that's something that we are thinking about, how to sort of, get rid of that bound, because that's the bound that we really hate, because, that's the one that that is sort of, causing all our tunings for the coupling. So we are really trying to see if, if we can somehow, remove those bounds on those couplings. Yes. So we are trying to maybe make the theory supersymmetric. That's so we are actually, Marcus, we are actually looking at your paper with Raman on, how to supersymmetrize the Goldberger-Weiss mechanism and, include the radion and have radion superfill. So it's a very useful, very beautiful paper.
It was a long time ago. Yes.
Okay, any questions from not Marcus?
During inflation, you need the Higgs VEV to basically sit at our current minima already, right? Or roughly.
That's true. Yes. Yeah. Otherwise, I would exactly. That's true. Yes.
Electroweak.
So having a realistic, yeah. So you're asking, can I actually make a realistic model of inflation? Yes. That's a good question. Yes. So it has to be a very low scale, right? So that is a challenge. That is a challenging.
So baryogenesis. Right?
Baryogenesis is going to be difficult. Yes.
How big is the S parameter in this model?
I mean, I think this is basically the standard model with, with the light dilaton. I mean, we know that, the radion doesn't give, I mean, it's not very much mixed with the Higgs. So,
but I heard techniquarks in a CFT with large N.
Right, but again, they are not what is giving rise to electroweak symmetry breaking. So I told you, I just call them techniquarks, which is the CFT matter. Yes. But they are not, I mean, the electroweak symmetry breaking comes from the Higgs. So they are not gonna cause any problem. Again, dilaton does sometimes give, like, Jack, you looked at it, we looked at it, but that's only when the mixing with the Higgs is pretty big. And
but if the Higgs couples to the techniquarks and gives them a mass, then they also contribute to S.
That's a good question. Yeah, so that's a good question. I mean, it does couple to that operator, yes. So you're asking, okay, so in the 5D picture, you're saying that I would have some sort of graviton loops. That's a good question. I don't know. I mean, obviously we were just assuming that, it's small, but I haven't thought, maybe graviton loops could be important. Okay. Because you're saying that we have this CFT picture where the Higgs operator is coupling to the to this CFT operator. Okay. But probably from that picture, we should be able to directly get an estimate for the S parameter, no? Somehow integrate out the CFT and. But you see, I mean, I don't see how I mean, you need to get the W and the Z, the W mu nu and B mu nu in it. And I don't see how how those would generate an S parameter. Okay, anyway, I don't know. We haven't thought, but my guess is there won't be.
You have a technoquark loop with a W and a B attached and some Higgses that couple to the technoquarks and break electroweak symmetry for them.
Okay, I guess I have to write out the full CFT effective Lagrangian, including the coupling to the W and the Z and C. Yeah, maybe. Yeah. We better check it. I agree. We better check it.
So if there's no more questions, let's thank Csaba again.